Hello, Murali. Murali? I'm audible.
Yes, ma'am, you are audible. Actually, just before Murli asked, can I start? I
yeah.
asked him, we'll just wait for a minute, so ma'am will join.
But it's not.
Maybe since I asked to wait for a few minutes, he
Yeah,
might
yeah,
be
yeah.
busy, ma'am. He'll be coming
Yes,
soon.
ma'am, I am available.
Yes, ma'am.
Yeah,
Yes,
yeah.
he's there.
You please start, Murali. Welcome to all of our second day webinar on queuing theory. Sorry for delay for 10 minutes, 15 minutes. Okay. Please, Murali.
Yes, ma'am, I will start sharing my screen.
Okay, okay.
Is the screen visible? Hello, is the screen visible?
Yeah, visible, but it's not visible clearly, Murali. Please
Okay,
zoom
ma'am.
in.
Yes, ma'am, I will do.
Now
is it visible on queuing theory? So I hope like yesterday's you have gone through with the 37 pages of PDF, and today's will be it will be still more interesting because we'll see how we can implement that 37 pages of content into solving of a problem. So please do get connect with the complete session of today so that you will get a complete knowledge of all different models that is available in the queuing theory. Okay, so before I'm starting up with this problems, I need to give some basic details. So I'll just share the whiteboard and give the particular details so that that will help you a lot in understanding the way in which the problem to be solved. So I'll be now sharing the white screen. Yeah, okay. Yeah. So most important thing is that apart from yesterday's PDF, what has been sent, one important note point is there that you need to note and is very important in point of view of examination, model papers and all. The thing is that they are asking this particular type of question. What is the probability of waiting time in a system greater than time t? That means a person is waiting in the system. What is the probability that his waiting time is greater than some particular time t? So you have a formula for that. I will be writing here. Please note it because it's not in PPT. So I'm asking you to note. So it is P of W greater than T, because here they are asking probability of waiting time W of the system which is greater than a time T, which is equal to e to the power of minus of mu minus lambda into T. So this is the formula. You know already mu is nothing but mean service rate, lambda is nothing but mean or average arrival rate. So T is nothing but the time. So this is how the probability of waiting time greater than the time T. Please note this. So I'll go to the next one. Okay. Mm. See, very important thing. Yesterday I told about steady state as well as transient state. I hope you remember that. See, if you consider a transient state, for example, so P naught, P1, Pn. So if you just know about, I told one thing yesterday, that is Pn of t. At the time t, the probability of having n number of customer in the system. Now P naught, the probability of being an idle time to server. That means server is idle. So P1, there is one customer in the system and he will be served. So what is the probability for so to happen? So similarly Pn. So now if it is considered as a non-steady state or transient state, we are having a relationship of P1 is equal to, please do note this, because it is very important in point of view of problem, as well as this is not covered in PDF, which I will be uh, sending for today or tomorrow. So P1 is equal to lambda naught by mu1 into P naught. Now P2 I will be telling. So P2 is equal to lambda naught lambda 1 by mu1 mu2 P naught. Now I hope you can only write what is P3 because it follows the same pattern. The only thing is lambda 2 will be additional here and mu3 will be additional here into P naught. So this is how you can frame your Pn also. And this is for very important. This is for transient state. And I told transient state definition in the last session. I'll repeat that. Transient state means it is the state in which the behavior of the entire queuing system is dependent on time. So this is the transient state. Now, what is the importance of having the steady state is that, so the above formulas will get converted in the steady state as follows. So you have P1 is equal to lambda by mu, because here in the steady state your lambda naught equal to lambda 1 equal to so on equal to lambda n, because they are all independent of time. So your lambda values and mu value remain same, they don't change with the time. So that's the main reason why I have taken instead of lambda naught lambda, instead of mu1 mu into P naught. Now if you can guess what will be P2, I think anyone can unmute and tell what will be P2 in the steady state, provided that in steady state lambdas all will be constant or equal and mu also will be a constant one. Please have a try for P2, P3 and so on. If you want, I'll write for P3 so that any of you can write for P2. So for P3 it was in the previous P3 it was lambda naught, lambda 1, lambda 2 and all three are equal to lambda. So can I write lambda cube here? Okay, so this is lambda cube divided by, there it was mu1, mu2 and mu3. Here I can write it as mu cube. So it is simply lambda by mu whole cube into P naught. Please tell anyone for P2 now because it is very easier. You are seeing the pattern of P1 and P3. So it will be very interactive session if I do in this manner. That's why I asked you to do. So please guess for P2.
Good evening, ma'am.
Good evening.
For P2, it's lambda square by mu square into P naught.
Yeah, perfect. So this is how we do for the steady state. So it is a perfect answer. So that's how you can do for Pn. It is lambda by mu whole power n into P naught. So this is very important. So for this pattern to get arrival as well as to understand about this thing, I have opened the whiteboard. Now we are ready for solving the problem. So I'll be coming back to the problem. So now you can by yesterday's knowledge as well as today's what I have explained, you can start up with the problem. Okay. So problem is this. So I have taken a simple problem, but with all explanation that is possible to solve any type of problem in the future. So the thing is simple. Here I am taking one-man barber shop according to Poisson process with a mean inter-arrival time of 12 minutes. Please do understand this problem completely because these are the only possible case that could be asked in your exam. Yeah, only possible case. Okay. So customers spend an average of 10 minutes in the barber shop. Only reading that first two statement, again can anyone guess what type of model it is? Because first important thing is you have to identify model. Is it MM1 infinite FIFO or something else? So that's very important here. Okay, so for now I will only tell the thing. See, it's a one-man barber shop. So server is one, so it will be MM1. And nowhere they have given that they have a restriction for the customer to get into the system. I actually, in practical case, this is not an infinite queue length, because barber shop will be having very less capacity for the person to just get set down. But here in particular question, they are in a intention that you have to treat it as an infinite. That's why they have not given that so or so is the maximum limit of person that is available to get seated. So I can consider this as an infinite queue length. So it is, the model is MM1 infinite FIFO. So okay, so they have given different conditions for which you need to get the answer through this MM1 model. Okay, so let me begin with the next one. Okay, the first and most important, city. So the problem that comes here is MM1 infinite FIFO. Now, yesterday I think hope you have gone with the PDF of 37 pages. In that, in one page, I have been given with a title called key points. So that key points is very important now, because see, here they have given with mean inter arrival time. So always mean inter arrival time is exponentially distributed and is given as 1 by lambda. So you have to take 1 by lambda as 12, not lambda. So 1 by lambda is 12. So you will be getting lambda as 1 by 12 per minute. Next, customers spend an average of 10 minutes in the barber shop. It means he is spending 10 minutes in the barber shop so that the next person can arrive after so time, after 10 minutes. Again, this is also inter-service time. So if the inter-service time is given, it is exponentially distributed with mean 1 by mu. So the value of 10 goes to 1 by mu. So it's very important, you have to take 1 by mu. Sometimes they give directly lambda and mu. So it's somewhat key and important point for you to get noticed. So you will be finding the value of mu. Okay, that is basic. Now we'll go to first one. So what is expected number of customer in the barber shop and in the queue? Okay, first I'll go to expected number of customers in the barber shop. It's a very simple thing. It is the expected number of customers in barber shop is nothing but barber shop here itself is a system, correct? So it is nothing but expected number of customer in the system. You have LS formula, please do apply. Lambda by mu minus lambda, you'll be getting 5 customers. So there are 5 expected number of customers in the system. So now expected number of customers in the queue. So how much number of customers are present in the queue? So it is L Q lambda square by mu into mu minus lambda. You'll be getting 4.17 customers. So if you were very active in yesterday's class, with this, what I can tell, this slide, you will be getting one definite doubt. If you got so, you will be asking at the end of the session, because I know you can take screenshot and think of it. Okay. So next one was that calculate the percentage of time an arrival can walk straight into barber chair without having to wait. See, barber chair, if a person has to enter straight, it means that nobody are there. You are the only person who has gone and nobody are there. Then only you will go and sit straight away in the barber chair without waiting. That means what? That means there are no customer in the system. Yes. So to do that beat one, we have that it's nothing but simply P naught, property of no customer in the system. It is nothing but you go straight away and sit in the barber chair. So as I told yesterday, very important thing, P naught is 1 minus traffic capacity or capacity utilization. So rho, that is 1 minus lambda by mu. So it is 1 by 6. So 1 by 6 into 100, you get 16.67%. So in the 16.67% of time, you can straight away go and sit in the barber chair without being waiting for even a single minute. So this is what the thing is. So C question. So for again and again, you can't scroll back in front. So I have typed the question also in this only. So the question C was, how much time can a customer expect to spend in the barber shop? It is nothing but what is the time he spends in the system, WS, 1 by mu minus lambda. So it is 60 minutes. You can convert as 1 hour. That D, as well as somewhat critical part. So please do listen again. So management will provide another chair and hire another barber. When he will do? When he is running his business in a profit manner. Is it not? Because if he is running in loss, why could he need to hire one more barber and give him salary, etc., etc. So it means there will be some condition for which the management is ready to provide another chair. If in a college there is a lot of admission than required, then only they will hire new professors or someone. If not, why they do so? Correct. So that's what that condition is there. That is what they are expecting from us. Okay. So when the customer's waiting time in the shop exceeds 1.25 hours, that means if the customer is waiting more than 75 minutes in his shop, then only he is ready to hire the one more barber. So that's the condition. So you can take it as WS because waiting time in the system is greater than 75. So I'll be taking 1 by mu minus lambda r is greater than 75. So from that, I'll find lambda r. Why lambda r? Because if a new server comes into the picture of a system, then arrival rate will have an influence. It is 100% because how I will explain you in an normal manner, because from yesterday I'm trying to attract you by taking some practical examples. So what the thing is, assume, don't assume barbershop, you directly assume there is an I can tell there is a company who is providing you with some tokens. Initially, it was only one token. You need to wait in a long queue for a long time and you have to take the service. Now, all of a sudden, if one more, what I can tell, one more person is ready to issue token, that means you will make two different lines. Na? So if you are making two different lines, then your waiting time reduces. Then you will have a tendency that you will rush into that system only, though there is some other alternative systems. That's how the arrival rate will change. So always, if this case comes, you have to take the new arrival rate lambda r. And my intention is finding the lambda r. Just you equate the equation, I got lambda r as 13 by 150. But that is not the question they are asking. They are asking average rate of arrivals increase. It means this new one minus the old one. So it will be 1 by 300 per minute. This is what the answer they are expecting. Okay. So next I'll go. What is the average time customers spend in the queue? Again, WQ they are asking. Straight away formula. So you can substitute and you get the solution. This is why I have given you for F. To solve Fth one, I have given the whiteboard formula. See, what is the probability that waiting time of the system greater than 30 minutes? So if the waiting time of the system is greater than 30 minutes, for that what is the probability? So that is very, very important. So there may be one question, then is it there any formula for probability of waiting time in a system less than some particular time? Is there any formula? So we will talk about that in the last session if you are really interested to know that. But this is important in the point of view of exam. So you just substitute. So e power minus of 1 by 10 minus 1 by 12 into here greater than 30 minutes they are asking into 30. So you'll be getting the solution. So this is what the thing. Next Gth one. Okay. This is again interesting question. Calculate the percentage of customer who has to wait prior to getting into barber's chair. If he has to wait means there should be something waiting time or not? Yes. So I have taken probability of waiting time greater than 0. That means other than 0, I should have some waiting time. Now I am in an intention to wait in the barber's shop. Correct. So W greater than 0. Is it not 1 minus W equal to 0? Because from the total system, if you consider the sum of probability of everything that is associated with the system equal to 1, you are subtracting 1 minus P of W is equal to 0. That's it. So W equal to 0, when is it possible? When you are the only customer who have entered, that is P naught. So that's why in the fourth step I have directly taken 1 minus P naught. So see, one important thing is P naught is 1 minus lambda. Then what is 1 minus P naught? Directly lambda by mu. That's what I have taken here. So P naught is 1 minus P naught is lambda by mu. So I have taken it as 83.33%. So next, last one, H. What is the probability that more than 3 customers in the system? Now you are entering the barber shop and you are finding the 3%. For that, what is the probability? So you want to know, because before you leave your home, you want to know at a particular time or particular system, what will be probability of having the 3 customers. So that's why I told this queuing system analysis and designing using particular model is very important. In some particular problems, I have listed in the yesterday's PDF. You can go it again today. You can go through once. So it means here probability of n is greater than 3. That means P4, P5, P6, so on, Pn. So finding that is difficult. So I have directly taken 1 minus of. So you are subtracting the probability that you don't require. So that is P0, P1, P2 as well as P3, because they are asking more than 3 customers, not 3 or more than 3. So you are subtracting these things. And now the today's formula comes to picture. I told. So in any of your queuing system problem, until and unless they mention the system is in transient state, you have a freedom to take it as a steady state. Because yesterday I told one important point, in steady state, every system after some particular amount of time will have a tendency to reach the steady state. And one more important thumb law in queuing theory is that whoever the customer is, as soon as he enter into the system, or as soon as he arrive into the system, he will be having the utmost tendency to get out of the system at his earliest. So these two are very important thumb rule based on which we are designing everything. So very important. So I'll be taking up that later on. So now, for now, you know what is the formula of P naught, 1 minus lambda by mu, and P1, P2, P3, I'm substituting, I'm simplifying. I'll be getting the answer as 0.48. I'll finish different other models in brief, because different other models, if you understood MM1 infinite FIFO model clearly, then other things are just a formula and substitution. Okay. So this problem, you have a special provision at the end. Any doubts regarding this problem, you are free to ask. Okay. So now you understood what is MM1 infinite FIFO model. So now I'll restrict the queue length, or I restrict the customer to enter into the system if my system space is running out. So that is called as model 2, that is MM1 KFIFO model. Yes. So here what is the thing? I am restricting the customers in the system, correct? So if the queue is full, I am not allowing any customer to enter the system. Okay. So this is again a difference equations. You no need to remember this, because with this 1 and 2 equation only we will obtain different other equations. So you no need to remember this equation. So you get P1, P0, these all things are just a derivation. I explained it orally in whiteboard also, these formulas. So I'll be going directly. You have LS formula. So average queue length, LQ is equal to LS minus lambda dash by mu. It's very important. It is called effective arrival rate, lambda dash. So if you want to learn more about lambda dash, tomorrow there is one problem in which there will be an usage of lambda dash. At that space, I'll explain everything in detail about lambda dash. For now, you have to take a screenshot of this whatever formulas I'm giving, because on these formulas which you take screenshot. Tomorrow again I will help you out how to solve using these formulas. Okay, right. So WQ is equal to, okay, anyway, again, this you know already, using little average waiting time in the queue using little yesterday we learned. Okay, so whatever you learned now, that only I picturized. Yes, so what is P naught, what is Pn? So why I have done in this manner, because there it was random, so here you will be getting at one space, you can take a screenshot. What will be value of P naught in KFIFO model? What will be the value of Pn in KFIFO model? So that's very, very important here. Yes. So then LS. So these explanation I gave in depth yesterday also, today also. So here you can just remember the formulas, because these derivations are again from the difference equation only you are deriving it. But formulas are the one that is majorly being useful in terms of problems. So you can take these screenshots. Yes. So I'll be waiting for some time. So lambda dash here is called as effective arrival rate. It is equal to mu into 1 minus P naught. Okay, so it is done, right? So these were about MM1 model. In MM1 model, the major thing was there were only one server. What if there are S servers in the system? So then you have a limitation. MM1 model cannot be applied when there are S, or not only if you are having on two server, then also any formula if there are even two servers. So that's very important. In the problem, if they have anywhere given that two servers, and if you used MM1, it is completely wrong. Okay. So now I'll go with the explanation of MMS. Then what I have to do for 2 server, 3 server, I can make a use of MMS model. Okay. Here I'll give the explanation of these terminologies. MM, because you know arrival rate as well as service rate are Poisson distributed, and Poisson distributed is a Marcos, continuous Marcos chain process. So we use MM. S, because there are S number of servers in the system. Infinite, okay, so for this model I'm taking infinite because it is of infinite capacity. Yes, so then you have FIFO. Done. Okay, now it is a multiple server infinite queue length model. Okay, see, yesterday I told one very key important point. See, if you want to run your business, by satisfying your customer in an effective manner, then always you should maintain in such a way that lambda should be less than mu. Okay, so presently we don't have time. So if at last we have time, I will tell why that is, because that is not the syllabus point of view, it is a business point of view. Why lambda should be less than mu. Okay, so that is the secondary. For this queuing model, lambda should be less than S mu, because there are S systems, correct? So S servers, sorry, S servers in a one system. In one system there are S servers, so S mu. Okay, so you have the values of P naught and Pn. So please do take a screenshot of this. You have in a single slide. So P naught, Pn, average number of customers in a queue, and already we have taken a problem of MM1. If suppose there are two servers, then instead of that formula you have to use this formula, that's all. But there are some logic things, only that logic things I will take up in the problem in tomorrow session. Tomorrow session very important. With these problems I'll be even taking model paper problems and previous year's solutions. So please do attend tomorrow's also. Okay, now you have LS, average number of customers in the system. So you have the formula, please do note it. Okay, so next, time, average time a customer has to spend in the system, and average time customer has to spend in the queue. So those two are also very important. So that's about your MMS, infinite FIFO model. Here KFIFO model, it means here there are S server and also my queue length is limited to K. That means after K, so K plus 1th person is not allowed to enter the system at any case. So that is what the thing is. So please do note P naught, Pn, So average number of customers in the queue, LQ, and EN, you have the last line of the formula. That is important. This is the derivation, how we obtained it. So then you have, again here lambda dash will come into picture whenever you have limited, when you are limiting the um, customer to enter into the system, then you will not have any freedom to use the actual arrival rate. Instead, you have to use your what I can tell, effective arrival rate. So that's where this comes to picture. Okay. So again, we have completed every model in detail with explanation of MM1 model. So please do start your work. Please take a calculator, pen, and start to solve this problem. Yesterday was level 1 problem. It was just a theory you can do directly. This is a problem. If you have understood that problem which I explained today, you are 100% correctly you have to solve this problem. Okay, I'll explain the problem first. So it is given that average number of arrivals per hour, very simple problem, please listen. So average number of arrivals per hour in an infinite capacity queuing system is 10, and the system is to be expected to have a service from single server. The customer is expected to spend about 9 minutes in the system. What is the capacity utilization of the above system? You have 4 options. Let me see who will solve faster and put in the chat box. Please do start solving. So by then I'll just take you into the revision and also help you how to solve this problem. Because solving this problem is nothing but having revision of whatever you have learned today. So please do take the screenshot and start solving. So by then we will learn. The first important thing in any problem solving of queuing theory is that you identify model. So now you have already 4 models and 4 different list of uh, um, formulas, and I told you to take screenshot. Now identify which model this question will fall under. Okay, then you identify different formulas, whichever formula is necessary for you. So then you try to find what is the capacity utilization. So please do start and take the and give the answer in the chat box. At the end, I'll again solve this problem in whiteboard also. Please no need to worry. So I'll open the answers you're giving. Okay, one has given answer C. Okay, let's wait till most of them give the answer so that let me see if there are other options also. And meanwhile, if anybody is having any doubts, they can also start asking about that problem as well as any other thing. And also, please first do solve that problem. You will only understand every process that we have done. So try that problem first. Okay, one more answer has come. Okay, it is B. So let's see if any other answer of A and D also would be appear here. Okay, B. Okay, right. Okay, let's see. Um, if any other options also comes, or you also like who has given C, B, you also keep trying whether your answer is right. You can also correct and repost your answer. Very simple. If you are facing problem in solving that question, you open the screenshot of problem. Okay, majority of these are coming. Okay, let's see if any other having option of A and D. So for now, I'll again open the quiz so that whoever has missed taking the screenshot can see this. So this is the question. So another 3 minutes I'll be giving, because last 10 minutes is for solving this quiz as well as doubt clarification. So please do try in another 3 minutes. Anybody are free to give any answer, because here there is no negative marking. So your any answer will be accepted, though it is right or wrong. So please do have a try, at least just solve something and give some answer whichever you get. Any one answer is A and D. No, again B. Okay. So the question I'll be explaining again. So because I don't need to waste time of 3 minutes, I'll be explaining so you can understand again and do the problem. So here given average number of arrivals per hour. See, it's an infinite capacity queuing system. Infinite capacity, so infinite FIFO model. So now, is it MM1 or MMS? That is what you need to find. You listen to the next line of this. And the system is to be expected to have a service from single server. So very simple. So from first 2.5 line, you were able to know that it is MM1 model. So now only have given int again. So with MM1 model, with all your available, if you just go with yesterday's 37-page PDF, you'll get answer for this question. One more hint. So you find capacity utilization. Okay, I'll give definition for capacity utilization. It is the ratio of average arrival rate to average service rate. That is rho is equal to lambda by mu. Rho is equal to lambda by mu. So please do now you try, because another 1 minute. This is what the question was. So okay. So it's C's and B's only. So I think if so is the case, then let me eliminate A and D for you. So please do tell answer between B and C. So A and D are gone. They are not the answers. So answer is among B and C. Now I think more the people can give your answers. B or C. For last 1 minute, this chance is. Please do try. At least your name will come in this chat list. Please try whether it is B or C. It's C only. Okay. So yeah, he's very confident because from think it has gone to C only. Okay. C. Okay, because of the C majority, I'll even eliminate B. So and the correct answer is C. Okay. Yeah. So answer is C. Now I'll tell how the answer is C. Okay. I'll again share my whiteboard. Okay. So I'll read the question. It's given that average number of arrivals per hour. It is nothing but average arrival rate. Yes. So I'll be taking the white screen here. So answer is considered as C. Okay, sorry. Okay. So given as lambda is equal to 10. Yes. So what else is given? So the customer is expected to spend about 9 minutes in the system. Yes. So 9 minutes in the system means WS equal to 9 minutes. Is it not? 9 by 60 hours. So 0.15 hours. So you have got the value of lambda to be 10 and WS to be 0.15 hours. Okay, so these two are ready now. So by little r, you can find what is LS, correct? LS is equal to lambda into WS. You get 10 into 0.15. Please do solve and anyone tell answer, because I don't have calculator here, because I'm straight away doing in white screen. Okay. So we know again LS as lambda by mu minus lambda. Yes. So please anyone tell the answer of LS. So, and also please check whether is WS 0.15, 9 by 60. Okay. Please do tell by unmuting because I can't again open because I'm doing in phone, so I can't again open WebEx and see. Okay. So it is simply mu minus lambda is equal to lambda by LS. So mu is equal to lambda by LS plus lambda. Yes. So I have lambda value as 10. Now you will be telling what is LS plus lambda 10. Please tell LS. See here I have again made it very simple. So 10 means it is 1.5. Correct. Yeah. So I have only taken what is LS also. At least please tell this. So 15 by 100, 6.67 plus 10, 16.667. Is it correct? So then they're asking row, it is 10 by 16.67. Or I can take it as 10 by 17 approximately. No, at least please tell the final answers so that you can give final touch-up. So it's simply 17 by 10. So you can take, sorry, so 0, 100, point, 17 5s are 85, 15, 588. Okay. So 0.588. Is it not nearer to 0.56? Sorry, 0.6.
0.6.
Yes,
Yeah.
your answer is 0.6. So this is the answer. So option C is correct answer. So I hope you also solved in the same manner. And if you have still more shortcut than this, you can also share now. So that's all for today. So I hope it was very interesting and clear. And you have lot more of interesting things like this in your tomorrow and the end session. So please don't miss to attend the tomorrow session. So now you can ask your doubts if you have any. Also, if you got any confusion still regarding this question, what quiz question we have solved now, you can ask now. Yeah, it's really great. In the chat box of Prakash ji, so they have tried in a very good manner. So in an practical case, they have given answer. They have not used any formula. So telling that there are average 10 users, each user uses 9 minutes. So maximum 6 users can use in the 54 minutes. So it is simply 6 by 10, so 0.6 they are telling. Okay, it's one try. So it's nice. So that's how. So you're thinking in a practical manner, or you're applying the same practicality and checking using the mathematical manner. So what I have done is completely using the mathematical manner. So I used all the formulas that is possible, and yeah, thank you. So if you have any doubts, you can just ask, or you have any feedback, you can tell. So anything is accepted. Yeah, they're telling about industrial applications, so real-time applications for whatever I'm doing. So to tell at the end of the session. So it's very important because see, one major application I told in between of solving of problem. See, in order for a person to appoint a new barber, I told at that time. So he can't straight away take a new person and appoint unless he know what is the practical situation that he's facing in his business. It's completely like business oriented. So whatever queuing theory you see is just you are dealing with the customers. So you deal with the customer. If you are running in a profit manner, means more the customers are attracted towards your service. So it means now I told he need to appoint a new barber. He won't come in a straight away manner. So uh, so 1 minute. So there was some chat. Yeah, sure. So they need application in some different field. Okay, nice. Yeah. See, there are some number of tasks that a research scientist get in his venue time. So there is you take a research office and the research scientist will be getting the number of data. So he completely deal with the data, he analyze the data and he work accordingly. Now, that research company will be in a safer side only if whatever the data they get, they handle it, they do the research on that, then they publish some resource from that. So now the problem that arises without using this queuing theory is that if lot the number of resources are coming and the efficiency of the research scientist, now you assume research scientist as a server and whatever the this one, whatever the applications or whatever data you are getting as a queue. So now, if that server is incapable of serving some particular thing, then the company or whatever the research organization will be there, they are unable to fulfill the requirement. So now, if you can appoint a new research scientist to do that work in an effective manner, you need to go with all these process so that they, in no case, should end up in a loss. So they should manage to get their data done in an effective manner. So I hope this was something different than what it was conventional. If any other doubts, you can tell. If not, we can conclude. So tomorrow's session will be completely on different problems. Completely tomorrow's session is on problems. So we will be solving everything that is associated with the problems with respect to your VTU as well as some practical problems also. If time is permitted, we will be taking up and we will be dealing with it and we will be applying these different models in this. Not only MM1 infinite model, every other models also will be taking up into consideration. So tomorrow's will be the end day as well as a very interesting day of these 3 days session. So please do attend and if you have any other queries also you can take up in the tomorrow's session. So thank you, ma'am. Thank you. I think today's week I have completed.
Okay, Murali. Yeah, anybody need that problem what you given on a quiz before quiz you are explain. Yeah, thing you one problem you told anybody need to explain once again. Have any doubt like that, right, Murali?
Yes, ma'am. Yes, ma'am.
Yeah, yeah. Anybody need for that problem explanation? You feel free to ask that. Yeah. Yeah, yeah. Are you sharing that solution, Murali, now today in the WhatsApp? What
Yes,
you
ma'am.
complete?
I'll
Yeah,
share whatever is done today.
yeah. I'm going to share it in the group. Okay. Yeah.
Yes, ma'am.
Gunavati, madam.
Yes, ma'am.
Yeah. Nobody's not asking question. He's ready to explain if you want that first question. But I think everyone understood that. We are going to wind up the session, ma.
Yes, ma'am. We'll wind up, ma'am.
Yeah.
Thank you, Murali.
Uh,
Thank you
uh,
for the explanations. It was actually
ma'am.
nice. Many have also commented that the session was nice and they can able to understand better.
Yes, ma'am. Yes, ma'am. I took everything in a practical manner so that they won't get bored in between.
Yeah, even they expressed their views regarding the presentation. Even
Yes,
they're
ma'am. Thank you.
happy in understanding the concept.
Yes,
Thank you
ma'am.
so much.
Thank you, ma'am.
Thank you for everyone, those who are attending today's session. We are expecting tomorrow also for supporting for everyone to attend tomorrow, only 1 hour. Yeah, he's going to solve all the different type of problems tomorrow. Then you are understanding more what you understood for today and yesterday. Thank you once again. Thank you and good night. Yeah.
Thank you, madam. Thank you, Rupa madam.
Thank you, sir. Everyone. Yeah. I'm going to share the PPT once Murali share in the WhatsApp, sir. Okay. Take care, Murali. Murali, I think is
Thank you,
already.
ma'am.
Yeah.
Thank you.
Thank you. Okay. Today, yes, yeah. Tomorrow we are sharing the joining link around 5 o'clock itself. Is it correct, Gunavati?
Yes, ma'am. Yes, ma'am.
Okay. Yeah, that live is going on, ma. YouTube stream.
Oh, okay, ma'am.
Yeah, showing that you are streaming the meeting to Facebook like that.
Okay. Okay, ma'am. Thank you all.
Okay.
As ma'am said, the link will be shared at the earliest. Even the feedback will be shared in the tomorrow's session. So based on the attendance and the feedback, the certificates will be issued. So all of you ensure that you attend tomorrow's session as well. Thank you all. Thank you, ma'am.
Thank you. I'm going to leave Gunavati and Murali.
Yes, ma'am. Yes,
Address
ma'am.
also. Okay. Thank you.
Yes, ma'am. Thank you.
Thank you, ma'am.
Maya, madam, please can you end this meeting?
Can I stop?
Yeah, yeah.
Yeah, okay.
Thank you.
Thank you.